So first of all, I would like to thank the organizers for the kind invitation. And let me clarify that this is one of the talks in this nice workshop and school, which is not on non-equilibrium physics. So I'll be talking about hard probes and hard probes in QCD, particularly in the context of electron-ion collider, but it is not non-equilibrium physics, okay? So what is the upcoming electron-ion collider? So it is another collider that hopefully will come up at Brookhaven National Lab. It will collide highly energetic electron beam with proton or heavy ion to take snapshots of nucleon at high accuracy, and this is what is called tomography of the nucleon. Tomography, you know what tomography is. You want to understand the three-dimensional structure of something, and you take multiple two-dimensional images, and from those collection of photos of two-dimensional images, you get an idea of the three-dimensional structure. So that is what electron-ion collider is going to do regarding the structure of the nucleons in terms of quarks and gluons. It will investigate various issues like how the quarks and gluons are distributed in space inside the nucleon, how do quarks and gluons bind together, what is the origin of mass of the nucleon, and how is the spin half of the proton is made from spin and orbital angular momentum of quarks and gluons. It will also explore the correlations between spin and orbital angular momentum of quarks and gluons and the intrinsic transverse momentum of these. And also it will investigate how does a dense nuclear environment affect quarks and gluons and their interactions. So this is a slide from Abhay Deshpande. It gives some details about this collider. It will work at very high luminosity, which is about 100 to 1000 times the luminosity of Hera, another electron-ion collider that is now no longer taking data. It will have a broad range in the center of mass energy from 20 to 100 GeV, and it can be upgraded to 140 GeV. It will use both unpolarized electron, proton and electron heavy ion collisions, and it can also use polarization. It will use a broad range in hadron species. From protons, it can go up to uranium. And there is a plan of having up to 2 detectors. So in this context, the first thing maybe you already know about it is the deep inelastic scattering. So proton is a bound state in QCD, this nucleon, and it's made up of quarks, antiquarks bound together by gluons. So this structure, internal structure of the proton is obtained using a hard probe. In this case, it is an electron. So actually the electron itself is not a probe. The interaction that we are talking of is the deeply inelastic scattering process. So this takes place via the exchange of a virtual photon. So this virtual photon is actually the hard probe. So electron emits a virtual photon with virtuality q square, which in this kinematics that we are interested in can be very large. However, the quantity called x, which is the ratio of q square by twice p dot q, is held finite. In this kinematical limit, what happens is that the virtual photon sees the quarks and gluons inside the proton. It does not see the proton as a whole, and it interacts with these quarks. Now the proton is Lorentz contracted, so it is a highly energetic collision. Proton is Lorentz contracted. You can think of it as a pancake in the transverse plane. So this virtual photon is coming and it is hitting this one of these quarks. And these quarks in the initial formulation, they were called partons. So partons is a collective term for all quarks and gluons. So what the virtual photon sees is a collection of partons moving with a fraction x of the proton momentum in the forward direction. And the transverse motion can be neglected. Transverse motion, the motion of these quarks on this transverse plane or the pancake can be neglected because this is much less compared to this longitudinal motion. So in the deep inelastic limit, the electron passes through the target at almost 0 time, and that is why it sees parton frozen in the transverse plane. And one has to remember that the electron can interact with the partons only if the impact parameter is less than the scale 1 by q. So q is the hard scale of the process. Electron parton scattering happens at a much shorter time scale than the hadronization scale of the proton remnant. So what happens in this deep inelastic scattering process is that this proton breaks up. So in the final state, there's a bunch of debris that you do not observe in your detector. What you observe is only the scattered electron. So it is the process EP going to E and X, and you don't care what is X, proton breaks up. So in this deeply inelastic kinematical limit, the differential scattering cross-section can be written as a product or as a factor of a soft part and a hard part. So what is a soft part? Soft part is a part that cannot be calculated using perturbation theory, and the hard part is calculable in perturbation theory. So this hard part is basically the elastic electron-parton scattering cross-section. And the soft part which is given here is called parton distribution. It is a function of X only. And then there is a sum over, incoherent sum over all types of partons. It is called flavor sum. Now what is this non-perturbative quantity or parton distributions? This is basically the probability density of finding a parton of momentum fraction X inside the proton. And in the original parton model which was proposed by Bjochen and Paskos, the partons or quarks were assumed to be non-interacting. And then what they have shown is that these parton distributions were functions of X, the ratio of Q square and twice P dot Q only. This is called Bjochen scaling. Okay. And these parton distributions are independent of the process, whereas this hard part is dependent on the process. So once you extract the parton distributions from one process, you can use the same parton distribution for another process. So these are non-perturbative quantities. It can be obtained or extracted using experimental data. That was the initial experiments which showed scaling of parton distributions. However, later experiments showed a scaling violation. So later experiments found that these parton distributions or something related to them which is called structure function, they are functions of both X and Q square. In fact, this scaling violation happens because of QCD interaction. Because these quarks or the partons, they interact with each other through gluons, and that is why this scaling violation happened. So this scaling violation can be calculated using perturbation theory or perturbative QCD. It is called Diglap evolution. Okay. Now, what are the processes by which you can see the interior structure of these protons? There are two main type of processes. One type of processes which we just discussed is where the proton breaks up. You bombard it with an electron and the proton breaks up. In the final state, there is no proton. However, in the final state, there is no proton and you observe only the scattered lepton. That is what I discussed just now. It is called deep inelastic scattering. There's another process which is similar to that where you observe one hadron in the final state. Okay, proton breaks up, you don't care what it is apart from one hadron. Maybe you can try to detect one pion in the final state or you can detect a kaon. So I believe many of the experimentalists who are sitting in the audience, they actually do it, but for LHC, so proton-proton collision. Here I am talking about electron-proton collision. So these kind of things or processes where you detect one hadron in the final state, it is called semi-inclusive deep inelastic scattering. Okay. So these semi-inclusive deep inelastic scattering probes transverse momentum dependent parton distribution or TMDs. So I am coming to that a bit later. However, there is another completely new set of processes where the proton remains intact. Okay. These kind of processes are called exclusive processes. So one such process is deeply virtual Compton scattering where you bombard proton with an electron. In the final state, you observe the scattered electron, one real photon and a proton in the final state. Okay, so the proton does not break up. So this kind of process also takes place via a virtual photon. The virtuality of the photon is basically the momentum transfer from the initial to the final electron. So this Q square virtuality is very large. But on top of that, there is another scale involved in the process, that is the momentum transfer from the initial to the final proton. That is, I denote by minus T. Okay. So at leading order, the process can be described by this diagram, which is usually called a handbag diagram. So this is the process I am talking of. Electron plus proton going to electron plus real photon plus a proton. But the momentum of the initial proton and the momentum of the final proton are not the same. There is a momentum transfer. And of course, this photon is virtual and this photon is real. So momentum transfer square in the proton side is P minus P prime square. Virtuality of the photon is Q square. Okay. And there is also a variable which is usually called a skewness variable, which is basically the momentum transfer from the initial quark and the final quark. Okay, so this momentum transfer is in the longitudinal direction. So at leading order, this kind of process, the amplitude for this kind of process can be factorized into two parts. One is a perturbative part. So this perturbative part is above. I haven't shown the electron line here. So this photon comes from an electron line. Okay, so initial electron and final electron. And then there is a blob, that lower part is a non-perturbative part. So this is also a factorized process at the amplitude level. The amplitude I can write as factored out into a perturbative part and a non-perturbative part. So this is the lower non-perturbative blob that I showed in the previous diagram. And this non-perturbative blob actually involves, if you try to calculate the amplitude, this non-perturbative blob involves some kind of matrix element of an operator like this. So these are fermionic operators. And this is a matrix element between the initial and final proton state, and then there is this kind of Fourier transform. Okay, so initial, what happens here is that this is the initial proton. So so one active quark comes out from the proton with some momentum fraction x plus xi. It interacts with the virtual photon, emits a real photon, and comes back to the proton with another momentum fraction x minus xi, because some momentum is carried by the real photon which is emitted. So as I said before, here there are two scales involved. Capital Q square, the virtuality is the large scale, and T or minus T, which is the momentum transfer from initial to final proton, that is the small scale. And deeply virtual Compton scattering kinematics is when Q square is very large but T is small. Okay, so in this limit, the blob, this entire thing can be parameterized in terms of certain quantities which are called generalized parton distributions. So this is the parameterization. For unpolarized proton, there are two generalized parton distributions. These are denoted by HQ and EQ. When the proton is longitudinally polarized, the generalized parton distributions would be H tilde and E tilde. You see the operator structure is different. And these matrix elements, as I said, these are called off-forward matrix elements because this proton and this proton have different momentum. So these generalized parton distributions, in short, GPDs, appear in amplitudes. So they do not have a probabilistic interpretation. We know the probabilistic interpretation of parton distributions. It is the probability of finding a parton or a quark with longitudinal momentum fraction x inside the proton. Okay. Generalized parton distributions do not have a probabilistic interpretation. However, if we take a Fourier transform in the transverse direction, delta pop, okay, these give the parton distributions in impact parameter space which have probabilistic interpretation. I'll come to it later. So GPDs have some relations to parton distribution. When there is no momentum transfer, they reduce to normal parton distributions, Q of x. This is the unpolarized parton distribution that I introduced earlier. And the GPD H tilde Q in the forward limit gives a polarized parton distribution. If you integrate these GPDs over x, you get the electromagnetic form factors. The unpolarized GPDs give F1 and F2, and these longitudinally polarized GPDs give GA and GP, the axial vector and pseudoscalar form factors. So these form factors appear in the parameterization of the local matrix element of this operator. So this is parameterized in terms of F1 and F2. You have seen this in Helsden-Martin. The first one you have seen in Helsden-Martin. Second one probably is not in Helsden-Martin, but this is similar for polarized proton. So as I said, the parton distributions that you see in deep inelastic scattering, they vary, they change with scale. Scale evolution, scaling violation was observed, that's called Diglap evolution. Similarly, these GPDs also have scaling evolution. However, for GPDs are functions of three variables, as I showed before. Parton distributions were functions of x only. However, GPDs were functions of three variables. They are functions of x, the skewness xi, and the momentum transfer square t. So the scale evolution is more complicated. On top of these, they have a scale dependency. And the scale in this process is Q square, the virtuality of the hard probe, that is the photon. So the scale evolution of these GPDs actually depend on which kinematical region you are in. When x is greater than xi and x is less than minus xi, The GPDs obey the same evolution equation as the parton distributions, that is the Diglap evolution equation. However, there is a new possibility when x lies between minus xi and plus xi. In this region, the GPDs obey another kind of evolution equation that is called ERBL evolution equation. People working in small x physics are familiar with this evolution equation. Okay. So that is all for GPDs. Why suddenly people became interested in these GPDs? So to explain that, I have to give you some idea of this nucleon spin puzzle. So spin of the nucleon or proton or neutron, they're half, we know. They're spin half objects. So this spin comes from the spin and orbital angular momentum of the particles that are inside it. So these are composite objects. They are built of quarks, antiquarks and gluons bound together. So this spin of the nucleon comes from the quark spin, also antiquark spin, quark orbital angular momentum because they move around, they are not stationary inside the proton. There's some orbital angular momentum. There's some intrinsic gluon spin and there's gluon orbital angular momentum. So everything coming together should give you half. So in a famous experiment which is called IMSc experiment in 1989, it was found that a very small fraction of this spin is actually coming from the quarks. Okay. So there's a lot of contribution coming from the gluon intrinsic spin and quark-gluon orbital angular momentum. So there are several issues about this equation that I have written here. Nucleon spin is half, irrespective of the scale you are probing it, irrespective of the virtuality of the photon probing it. Okay, nucleon spin is just half, that we know. However, the contribution, each of these contributions on the right hand side, they will depend on your probing scale. They will depend on the scale of your hard probe. Okay, each of the quantity on the right hand side will depend on Q square, whereas the quantity on the left hand side is independent of Q square. So somehow the Q square dependence on the right hand side should get cancelled. Okay, that is a fundamental property of QCD. So that is one thing. The other thing is that although we understood from here that significant contribution comes from the gluons as well as the orbital angular momentum, there is no direct way to measure the orbital angular momentum contribution of the quarks and gluons, although the intrinsic spin contribution of the gluon can be measured in experiment. For example, polarized proton-proton scattering experiments, for example at RIC, so it has been measured. So there are lots of activities how to measure this orbital angular momentum or how to get an idea of what is the contribution of this quark and gluon orbital angular momentum.
But this individual decomposition is always a function of the gauge. One has to do a gauge fixing.
Yeah, so I just skipped that topic. So there is another issue with this decomposition. I will briefly probably talk about it on a later slide. For a long time, people were confused as to whether you can separate the orbital angular momentum part into a quark part and a gluon part in a gauge invariant way, because we are doing QCD, it is a gauge theory. So whatever observable you have, suppose you measure something in experiment. Experimentalists do not know anything about your gauge choice, right? Gauge choice is purely a theoretical thing. So whatever you measure something in experiment must be invariant under gauge choice, okay? So people thought that you cannot actually separate the orbital part into quarks and gluons in a gauge invariant way. Okay, so actually it is a sum of three quantities on the right hand side. There's a quark intrinsic spin, gluon intrinsic spin, and a total quark plus gluon orbital angular momentum. However, there have been a lot of activity in the field in the past 10 years, and it has been shown that indeed it is possible to separate these quantities in a gauge invariant way. And there are different versions of this sum rule, and people have found out how to connect the different versions. Okay. So I have another slide on that. Yes, any question? Right. Quarks are also fermions, yes. Yeah, so this quantity is not the quark spin. Okay, this is contribution of quark spin to nucleon spin. It is called distribution, spin distribution. Okay, individually one quark has spin half, that's right. Okay, but inside the proton there are many quarks, right? So contribution of all those quarks to the spin of the nucleon, that is what I am talking of. Yeah, gluons are also many. Why gluon spin should be 0? Gluon has spin 1, right? And they are also moving around. There's also orbital angular momentum, okay? And worst thing is that you don't even know how many quarks or gluons are there in your proton, right? Why don't you know that? That's right. So number of quarks and gluons that you will see inside the proton will depend on the energy of your probe. Okay, so these gluon intrinsic spin, proton intrinsic spin, proton helicity, gluon helicity, how do you measure that? In experiment, people measure that in polarized scattering. So for example, you can polarize your electron and proton, and these kind of collisions give you some handle on what is called double longitudinal spin asymmetry, and this is sensitive to the intrinsic spin carried by the quarks. If you bombard polarized proton with polarized proton, it is sensitive to the intrinsic spin of the gluons. In fact, RIC data shows quite significant contribution from gluon, and several lattice calculations of quark and gluon angular momentum is also there. So gluon intrinsic spin is about 20%. So this is a recent review article that gives you the status of lattice calculations of the proton spin decomposition. According to this review article, the total quark angular momentum contribution is about 54 to 57%. Total gluon angular momentum is 38 to 46%, and quark orbital angular momentum is about 13 to 18%. But still the question remains, how to measure orbital angular momentum of quarks and gluons experimentally, and what is the role of intrinsic transverse momentum? Here comes the GPDs. So in 1997, Jiangdong Ji showed that these two GPDs, HQ and EQ, that I introduced earlier, if you consider these GPDs in the forward limit, you multiply them by x and integrate over x, you get 2 times the total angular momentum carried by the quarks. Actually, this is equal to sum of two gravitational form factors, AQ plus BQ. So these AQ and BQ are the form factors of the energy momentum tensor. So this is the energy momentum tensor of QCD. You take a matrix element of the energy momentum tensor between proton states. You can parameterize it in terms of some form factors which are called gravitational form factors. Okay. So AQ and BQ are two gravitational form factors. But what is important, this is called G's sum rule. This is called second moment. You multiply by x and integrate over x. The second moment of HQ plus EQ is 2 times JQ. JQ is the total angular momentum carried by the quarks. Quark intrinsic spin plus orbital angular momentum. So that means if you perform an experiment and somehow can extract these GPDs, from there you can get some idea of the orbital angular momentum contribution of the quarks. Similarly, you can construct gluon GPDs also. So if you can have some process or you can do some experiment which is from where you can extract the gluon GPDs, then on the right hand side you will have 2 times JG. From there you can extract what is the contribution from the orbital angular momentum of the gluons. So that is why people suddenly became interested in this exclusive process, deeply virtual Compton scattering and the generalized pattern distribution. That is one of the reasons. Okay. So this is the other, okay, so this is a small discussion about the two sum rules. So GPDs help us to understand how proton spin is made from quarks and gluons. So this sum rule that I showed earlier is called Jaffe-Monohar sum rule, and this sum rule is called G's sum rule. Okay. So there were lots of discussions about what appearing in this G's sum rule, this JQ, whether it is equal to half delta sigma plus LQ here or not. There have been lots of discussions in theory in the past decade, and after lots of effort, this has been sorted out. It is not always the same, okay? So, but there is some connection between the two. Now let me come to these gravitational form factors. As I said, gravitational form factors are form factors of the energy momentum tensor. You are familiar with the energy momentum tensor, right? So energy momentum tensor of QCD, since you know QCD Lagrangian, you can calculate the energy momentum tensor. So you can parameterize the matrix element of the energy momentum tensor in terms of 4 form factors, which are usually denoted by A, B, C and C bar, or sometimes this C is also called D. So we usually choose Rayleigh frame where the off forwardness of this initial proton and final proton is in the transverse direction. And these gravitational form factors, in short, I am calling them GFF, is basically giving how matter couples to gravity, okay, because it's the form factor of the energy momentum tensor. Now, what are the significance of these gravitational form factors? A and B are related to mass and angular momentum of the proton. So, A is actually related to the mass of the proton also, we are going to see that. So, this is the G sum rule which I just said. So, H and EQ are related to form factors A and B. So, there is conservation law. So, conservation of energy momentum tensor, there are various conservation laws. So, these conservation laws give you various constraints on these gravitational form factors. First of all, the gravitational form factor A at 0 momentum transfer, when we sum over all quarks and gluons, should give you 1. This is nothing but momentum conservation. Similarly, B summed over quarks and gluons at 0 momentum transfer should give you 0. This is vanishing gravitomagnetic moment. C bar form factor at non-zero momentum transfer, if you sum over all quarks and gluons, should also give 0. This is a consequence of Poincare invariance. This is because the total energy momentum tensor of QCD summed over all quarks, antiquarks and gluons is conserved. As a consequence, you can prove that the total C bar at some momentum transfer T should be 0. However, individually C bar Q and C bar G can be non-zero, okay, because individually the corresponding energy momentum tensor are not conserved. Only the sum is conserved. The interesting thing is that the fourth form factor CQ square is not related to any Poincare generators and there is no constraint on that.
What was the C bar concept?
So C bar form factor, so this total C bar quarks plus gluons should be 0 because del mu T mu nu is 0. Okay, it is a consequence of that. However, the quark part, so energy momentum tensor can be separated into a quark part and a gluon part. So you can define quark form factors and gluon form factors. Individually, quark and gluon C bar should be can be non-zero, okay, because individually it is not constant. However, CQ square is not related to any Poincare generator and it is unconstrained. And in fact, this form factor is quite interesting. So this is another area where there's a lot of activity in hadron physics is there these days. So this is the pressure mechanical properties of the proton. There is the energy and pressure distributions inside the proton due to these quarks and gluons and their interaction. It is this GFFC that has been found to be related to the pressure and shear force distributions inside the nucleon. So there's a lot of literature. One very popular review article is by these two authors in IJMPA in 2018. So mostly people work in bright frame, that is also called the Nucleon rest frame. This is a popular choice for the analysis of form factors. And one performs a 3-dimensional Fourier transform of the form factors. This thing you have done in, again, Halzen and Martin. So when you have this elastic scattering chapter in Halzen and Martin, if I remember correctly, it is chapter 8. There they discuss first the elastic scattering and then the deep elastic scattering, and then there are this electromagnetic form factors, and they discuss the charge distributions, right? There they do the Fourier transform. So this is the same thing here. So you have a form factor and you take a 3-dimensional Fourier transform of it to go to the position space. In fact, in position space, EMT, the energy momentum tensor as a function of R can be written in this way, where the first term is the energy density, second term is the isotopic pressure, and the third term gives the anisotropic pressure, okay, pressure anisotropy. And we can extract these quantities using these gravitational form factors, because gravitational form factors are just the matrix element of the energy momentum tensor.
Here, of course, there is no relation between the pressure and the energy density. It's not a thermodynamic system.
No, it's not a thermodynamic system. It's just mechanical pressure and energy density. Yeah, independent. So this is the isotopic pressure distribution. So this is the radial pressure and there's tangential pressure. There's 2 tangential directions. You are considering 3-dimensional spherical system. So there's 2 tangential directions. And this is the pressure anisotropy, which is the difference between radial and tangential pressure. So using the earlier gravitational form factors, you can express all these densities, pressure and shear densities in terms of those gravitational form factors, or rather Fourier transform of the gravitational form factors. Okay, this is what started the excitement in this field a few years ago. And then there was an extraction from the JLab group in 2018, who actually extracted the gravitational form factors from JLab data. Okay, you know, JLab measures this DVCS. It does this deeply virtual meson production or DVCS experiments. From there, it can extract these GPDs. And if you remember the properties of GPDs that I showed in one of the slides, moments of GPDs are related to form factors. Okay, so from there they can also construct these form factors, and they have plotted the pressure distribution constructed from the D term as a function of distance from the center of the nucleon. And what they have obtained is a curve like this with some error bar. So if I remember correctly, the green error bar is the error bar contained from the JLab 6 GB experiment. And then green one is the 6 GB experiment, blue one or greenish blue one where all the experiments before this 6 GB experiment were concerned, and the red one is a projection for the 12 GB. So you see, near the center, the pressure is positive and can be pretty high. You cannot see the unit from here, but the magnitude of this pressure near the core of the nucleon seems to be higher than the most dense object, that is a neutron star, and average peak pressure is as high as 10 to the power 35 pascals. However, as you go towards the periphery of the nucleon, the pressure distribution becomes negative. Positive pressure means it is a repulsive system, and negative pressure means it is an attractive system. So this is what you expect in a bound system. If the pressure is throughout attractive, then the system will collapse to the center. If it is throughout repulsive, then it will just tear apart. Okay? So that is why this kind of distribution is expected. It is repulsive near the core, but attractive towards the periphery. Okay, this also connects a set of collider observables or GPDs to the investigation of the equation of state of neutron stars. Okay, because it gives an idea of this pressure and energy distribution of a highly dense object. That's a very interesting article here. They also plotted the shear distribution or pressure anisotropy, and it is a curve like that. So as I said, JLab result triggered a lot of interest. There are lots of theoretical model calculations of pressure distributions. However, most calculations are done in bright frame and they are subject to relativistic corrections. So bright frame calculations and three-dimensional Fourier transforms have some problem. You have to incorporate the relativistic corrections. So these bound states of quarks and gluons, protons, neutrons, they are relativistic systems. And that picture is a little bit messy if you do a three-dimensional Fourier transform. So some other people introduced two-dimensional distributions in light front formalism. This is because transverse Galilean symmetry on the light front, light front transverse boost is Galilean, like non-relativistic. And this is free from relativistic corrections. However, these two distributions can be established also through Abel transformation. A little bit more detail about the problem of three-dimensional densities. So the problem of defining these pressure, shear, and energy distributions in 3 dimensions in bright frame was discussed by several articles around 2021. First one was Bob Jaffe, and then there's a detailed article by Fries and Miller. So what happens here is that the coordinate r in the Fourier transform has to be defined with respect to some location, right? With respect to some location of the system. So this means that we have to construct a localized wave packet whose center is the reference point with respect to which you are defining r. Okay, you have to have some kind of center. Now in quantum mechanics, we know that more precisely one tries to localize the system, the higher are the momentum components one has to introduce in the wave packet. This makes the relativistic corrections larger and larger because you have to incorporate larger and larger momentum components to more and more localize your system. Okay, so relativistic corrections become larger and larger. So this picture is not very accurate for a system having a size of the same order as Compton wavelength. This is what we are talking of, the nucleon. The relativistic corrections in this case even become model dependent of the wave functions as Lorentz boosts depend on the dynamics of the system. So this paper has a detailed calculation on that. Instead, one can define two-dimensional light front distributions where Fourier transforms are taken with respect to transverse momentum transfer. Such distributions are free from relativistic corrections as transverse boosts are Galilean or free from dynamics in light front framework. Okay, so those of you who are interested can see these references and also this one. So in two-dimensional light front distributions, what one does is that one usually chooses what is called Rayleigh frame where delta plus is 0, the light front transverse coordinate, the momentum transfer is 0, and one defines the Fourier transform in the transverse direction, okay, with respect to the transverse momentum transfer. And you can define the two-dimensional distributions in this way. This is the 2D Galilean energy density. These are two-dimensional pressure distributions and pressure anisotropy. So as I said before, for stability, this pressure distribution have to obey this kind of rule, which is called von Laue condition, which is integral dr 0 to infinity r square pr equal to 0 and the corresponding 2D version. So this basically ensures that the pressure distribution has a node where it has to cross the 0 axis. It cannot be throughout positive, it cannot be throughout negative. So JLab pressure distribution satisfies that, and in some simple model calculations both in 2D and 3D, people have shown to say that it satisfies the von Laue condition. How much time do I have? Still some time, yeah. So I have talked about some particular objects like GPDs and pressure distributions. So these are all part of the three-dimensional structure of the nucleon. How to understand the three-dimensional structure of the nucleon in terms of quarks and gluons in position and momentum space. So the most general object that gives us maximum information in this direction is called Wigner distributions. Again, Wigner distribution is basically a Fourier transform of something else called generalized transverse momentum distribution. So I am coming to that, but what is the Wigner distribution? It is a distribution of, for example, a quark inside a nucleon carrying a momentum fraction x, transverse momentum kt, and situated at a impact parameter or transverse position bt from the center of the nucleon. So it is a 5-dimensional object, x, kt and bt, 2 kt and 2 bt. So these Wigner distributions are related to all the other objects that people can measure experimentally. For example, if you integrate over kt, you get Fourier transform of GPDs, which are called impact parameter dependent parton distribution. So if you integrate over all kt, you are left with a 3-dimensional object, functions of x and bt. These are called impact parameter dependent parton distributions. They are nothing but Fourier transform of GPDs. If you integrate over x, you get basically Fourier transform of form factors. Again, from here, if you keep kt and you integrate over bt, you get what is called a transverse momentum dependent parton distributions. That is basically distributions which are functions of x and kt. If you integrate over kt, you get a function of x only, that is nothing but the normal parton distributions that I talked about in the context of deep elastic scattering. So generalized parton correlation functions are the most general correlation functions in the hadron, often called the mother distributions. As I said, both GPDs and TMDs can be obtained from them. If we integrate GPCFs over the minus component, you get a correlator that is parameterized in terms of generalized transverse momentum dependent parton distributions. And Fourier transform of these GTMDs are the Wigner functions. Now these generalized transverse momentum dependent parton distribution actually contain an operator which is bilocal. So theoretically you need gauge link for gauge invariance. And depending on your gamma matrix structure at leading twist, there are 3 kinds of gamma matrix structure in such matrix element. One is gamma plus, one is gamma plus gamma 5, and that is I sigma j plus gamma 5. And these kind of correlators or matrix element that I have written here, so this is the gamma that I am talking of. So gamma can be gamma plus gamma 5, or I sigma I plus gamma 5. Depending on that, this matrix element can be parameterized in terms of these GTMDs. So these quantities are GTMDs, F11, F12, F13 and so on. So these GTMDs are functions of all these variables, x, I, kt square, kt, delta t square and eta. So eta basically gives the direction of gauge link. Now let me introduce Wigner distributions. Wigner distribution is a very old concept in starting from 1932 by Wigner in the context of quantum mechanics. So it is something like a quantum mechanical phase space distribution. So if you consider a one-dimensional quantum system with a wave function psi of x, the Wigner distribution is defined like that. Fourier transform of psi star and psi, but the Fourier transform is with respect to the difference in position of these two fields, eta. Okay. If we integrate over p, we get a positive definite coordinate space density. If we integrate over x, we get a positive definite momentum space density. For arbitrary p and x, of course, you can understand Wigner distribution is not positive definite, because in quantum mechanics, you cannot define x and p simultaneously. So it does not have a probabilistic interpretation. However, it can be used to calculate the average of observables. Okay. Now, in this paper, they have introduced a similar Wigner distribution for quarks and gluons inside the nucleon. So this is similar to the quantum mechanical phase space distribution of quarks and gluons inside the nucleon. So you introduce a Wigner operator like that. So for gauge invariance, since this is bilocal, so this x is different from this x, or this position is different from this position, you have to introduce a gauge link. And then you can integrate various quantities, like you integrate dk minus, you get a reduced Wigner distribution. And then you can also get, in light front framework, you get a 5-dimensional Wigner operator. This is what I introduced pictorially at top of those diagrams. So this Wigner operator is basically a function of x, b pop and k pop. So Wigner distribution for quarks are functions of x, b pop and k pop. So what are b pop and k pop? So one has to remember that b pop is a conjugate, it is a position operator conjugate to delta pop, which is the momentum transfer between initial and final quarks. Okay. And k pop is kf pop plus ki pop. So this is the average transverse momentum. So b pop and k pop are not directly Fourier conjugate to each other. However, they do not commute, so actually they are subject to uncertainty relation. So one can integrate, as I said pictorially, one can integrate these Wigner distributions over various things. So this is the definition of Wigner distributions. So Wigner function is basically a matrix element of the Wigner operator. So if you integrate over b pop, one effectively sets delta pop equal to 0 and you get TMD correlator. If you integrate over k pop, you set z pop equal to 0, one gets the 2-dimensional Fourier transform of generalized parton distributions, which are the impact parameter dependent parton distributions. One can also have some mixed distributions. So these Wigner distributions can be calculated in various models. There are quite a lot of model calculations. You get a very interesting picture of these quarks and gluons inside the nucleon and their dynamics. Because as I said, there are different Wigner distributions. Okay, each of these Wigner distributions give you different information about the quark and their correlations. Okay, quark angular momentum, spin, orbital angular momentum, different kinds of correlations. For example, this is a model calculation when you look at an unpolarized quark inside an unpolarized nucleon. How is that quark distribution looking like in the transverse position space? You take a slice of the nucleon, how are these unpolarized quarks distributed in the transverse slice? So this is a picture of that. If you take a longitudinally polarized quark inside an unpolarized nucleon, how will it distribute it? If you take a slice of an unpolarized nucleon, you look at a longitudinally polarized quark distribution. You see this is bipolar. This has only one peak, this has two peaks. So this is because of the spin and transverse angular moment or transverse momentum correlations. So as I said, there are different kinds of Wigner distributions. You can look at unpolarized quark inside unpolarized nucleon, unpolarized quark inside longitudinally polarized nucleons, and so on. If you integrate, so these are related to these GTMDs that I introduced earlier, or rather the Fourier transform of it. So rho u is related to F11. So if you don't remember what are these F11s are, I introduced them here. Yeah, these are the GTMDs. Okay. Now what I am talking of is that I am connecting the Wigner distribution to the Fourier transform of these quantities on the right hand side. So rho u is related to F11. And if you integrate this F11 over B pop, you get the unpolarized TMD. If you integrate F11 over K pop, you get the GPDH. Similarly, G14 is related to rho LL. You look for a polarized quark inside a polarized nucleon, you get rho LL. And this is related to this helicity distribution of the quarks as well as this GPD H tilde. And now you can define this orbital angular momentum. So from the G's thumb rule, you can get the orbital angular momentum in terms of the GPDs H, E and H tilde in this way. Okay, H tilde is basically the quark helicity distribution. So if you take it out from the total quark angular momentum, you get the quark orbital angular momentum. On the other hand, from the GTMD F14, you can also get the orbital angular momentum. This is called canonical orbital angular momentum. And from the GTMD HG11, you can get an idea of the spin and spin orbit correlation inside the nucleon. Okay, so should I get into TMDs or should I skip it?
Just quickly, otherwise it will take it.
Okay, so I'll just give 2 slides on TMDs because I mentioned TMDs, transverse momentum dependent parton distributions. So TMDs gained importance from, again, some experiments. Back in 1990s, what people saw was that they, for example, bombarded proton with proton and they polarized one of the proton beams in transverse direction, okay? Unpolarized proton bombarding with transversely polarized proton beam. And in the final state, they were looking for a pion, for example. What they found was that this cross section depends on whether your proton is polarized up or whether it is polarized down. Intuitively, it is very puzzling. Why it should depend on the direction of polarization of the proton. But that's how it was. Okay, and this is, you can define something called single spin asymmetry, which is basically d sigma up minus d sigma down divided by the unpolarized cross section. And this is a result from Fermilab in 1991. You see in some regions, this asymmetry, this quantity is as large as 40%. And these kind of asymmetries cannot be understood in terms of those normal parton distributions that I introduced earlier. You have to take into account the transverse motion of the partons. And these are the transverse momentum dependent parton distributions or TMDs. Unless you incorporate that, you cannot explain this. And these TMDs appear in specific processes, for example, in semi-inclusive dim elastic scattering that I talked about earlier, or in Drelian process. And basically here people can write this cross section in terms of these TMDs. And again, some of these TMDs, so there are different TMDs and different TMDs have different physical interpretation. For example, there's one particular TMD Sievert's function, which again people have shown is related to the orbital angular momentum of the quarks. And this slide gives you a summary of different physical interpretation of these TMDs. So this is unpolarized TMD, you are looking at unpolarized quarks inside an unpolarized nucleon. This is helicity TMD, you are looking at longitudinally polarized quark inside an unpolarized proton. And the Sievert's function is when you are looking at unpolarized quark inside a transversely polarized nucleon, but the quark has some transverse momentum. Okay, and you extract the TMDs, for example, from the azimuthal modulation of the final state that you are observing. Okay, for example, you are observing a pion in the final state. So how is this pion distributed azimuthally? From there, you can extract different TMDs. So I'm skipping going into details of that. So all these things that I mentioned in this talk, the GPDs, TMDs, Wigner functions, all these things, they are basically parts of an elephant. So we are similar to these blind people. We cannot see the elephant. What we are trying to do is that we try to feel different parts of the body of the elephant. Some of us are grabbing the teeth, some of us grabbing the tail, and some of us touching the body and so on. And from the combined information of all of us, we will eventually find out the shape of the elephant. Okay, thank you.
Thank you, Asmita, for this nice presentation. So any question?
Hello, ma'am, you showed a pressure distribution as a function of R inside the nucleon, and it said it's a isotropic pressure. So it depends only on R. My question is, can we define a bulk pressure here?
Can we define what?
Bulk pressure inside this nucleon.
What pressure?
Bulk pressure.
Bulk pressure.
Yes.
Yeah, so bulk pressure, in a sense, these are distributions inside the nucleon. So what do you mean by bulk pressure?
Usually in hydrodynamics, we define isotropic pressure plus some correction term as a bulk pressure.
Yeah, that is a different kind of pressure. What
Okay.
you are talking of, the hydrodynamical pressure, that
Yeah.
is a different quantity.
Because there is a equation of state that relate pressure and energy density in hydrodynamics.
Yes, that is true. So the pressure and energy distribution that comes in hydrodynamics, that is, I believe it comes because of some temperature, right?
Yes. Yes.
Yeah, so that is a different reason for the pressure, and so that is a different origin of the pressure and the energy distribution. Here, I am talking of pressure and energy distribution coming from quark-gluon interaction at 0 temperature.
Okay. Thank you.
Yeah.
My question is also on the pressure distribution. So in the curve which you showed, the repulsive part has more peak compared to the attractive part. Is it due to confinement or something else is going on?
Yeah, so the combined nature gives confinement basically. The entire positive peak and negative peak together gives confinement.
Not just the, okay.
Okay, yeah.
I have two questions. One is about the pressure part only. You show that there are two parts. One is for repulsive, another one is attractive, right? Can't we just have simple attractive like what to say 1D box or like that? Can't we have a potential and the pressure like that?
Yeah, as I said, then the system will just fall into the center. It will collapse, right?
Because anyway we have a Coulombic repulsion, right? So
yeah, so we have a Coulombic repulsion, but it is not only Coulombic interaction that we are talking of here. It is called QCD interaction, right? Quantum chromodynamics. So whatever pressure and shear that I was talking of is purely coming from the strong interaction, QCD interaction. It is not due to electromagnetic interaction. That is what I was talking about.
then I have another question. You talked about parton transform, parton transform direction something.
Parton transverse momentum.
Transverse momentum.
Yeah.
What do you mean by that parton transform momentum?
Yeah, so initially I showed you a picture of the proton, which is a pancake, right? Quarks and gluons are on the pancake. They are frozen in transverse direction. But in reality, they can move also in the transverse direction, right? Proton is a 3-dimensional object. Okay, you consider a ball or something. So there are tiny, tiny quarks inside it. They can move in any direction. They can move in the direction of the proton. Proton is moving in some direction. Of course, quarks inside are also moving with the proton in that direction. But apart from that, inside the proton, they can also move in some other direction. So those are the transverse direction. Transverse to the direction of motion of the proton.
Yeah, so I have a question about this GTMDs. So did anyone study the evolution of GTMDs? Because of course, when you say you could integrate out one of a variable to get to PDF or TMDs, and of course it works kind of naively, but of course TMDs and GPDs have different functions. And so the GTMD has to have even more complicated evolution.
Yeah, GTMD evolution is expected to be more complicated. As of now, I don't remember of any reference which has studied GTMD evolution, but there may be some. I can come back to you later. But it's not very much explored.
Or we have considered.
We are not considering what?
I mean, if you are talking about spin of the quarks and also the orbital angular part. So, I mean, the usual LS coupling that we used to know in quantum mechanics, those are not going to play any role. I mean, the way you divided different spin contribution, are they scalar sum or direct sum? Or, I mean,
yeah, so these are basically not, this is not an operator equation, okay? So in quantum mechanics books, what you have is J equal to L plus S, that is an operator equation. The equation that I wrote down is not an operator equation. They are equation at a distribution level, okay? So each of these quantities is a scalar. So it is a scalar sum.
So here we should not expect any LS coupling kind of stuff because there can be orbital angular momentum of quarks and also spin.
Yes, so L dot S kind of terms. Yeah, L dot S kind of terms do not come at the distribution level.
Oh, okay.
Okay.
Is there any reason for that? Why they don't come in the distribution level?
Yeah, so basically these are the quants. So that is precisely because you define the total angular momentum as a vector sum at the operator level. J equal to L plus S.
Yes.
Okay, I think it is related to that.
Okay, so if you have any question, you can discuss during coffee break. So let's answer.